Hi everyone. This video is going to go over the concept of limiting reactants, or what do you do when you're given the amounts of more than one reactant. So in our previous adventures in stoichiometry with reaction equations, we're usually given an amount of one reactant and then told the other reactant is present in excess. In other words, the one we're given is the one that's going to run out. That's going to determine how much is produced. Everything's pretty straightforward. Now we have to deal with the fact that what happens if we're constrained by how much of each of the reactants we have on hand, all right? So there's a calculation to do this, which will involve the mole concept, as will probably not surprise you. So let's work through an example to see what that looks like. So we're given a reaction equation. This is butane reacting with oxygen, yielding CO2 and water, and it's been balanced for us. And we're given 3 moles of the butane, the C4H10, and 6 moles of the O2. How many moles of CO2 are produced? Let's tackle that question first. How many moles of the CO2 are produced? One of the things I like to do is organize my data underneath my reaction equation. So we've got 3 moles of the C4H10, and we have 6 moles of the O2, right? And we're asked how many moles of CO2 are produced. So I'm going to put a question mark moles there. And one of the things that we notice right away is that everything's in moles, right? So that means everything's going to be a one-step conversion, which makes things easier from calculating. It's not what we would normally do in a lab setting where everything's in grams. But since we're just looking at this as an exercise, everything's given in moles, everything's being asked for in moles. So one-step conversions all around. All right. Because we have amounts of both reactants, we have to do the calculation twice. So why is that? Because one of them is going to run out and we don't know which one. So we're going to start with this one, the C4H10. The reaction equation tells us for every 2 moles of C4H10, there are 8 moles of CO2 produced. And I'm getting that from the reaction coefficients here, which, by the way, sometimes we get sloppy in chemistry and people refer to these numbers as the number of moles, like 2 moles of C4H10 and 13 moles of O2 react. But remember, those are just the ratios in the reaction. That's not how many you actually have on hand. We actually have 3 moles of C4H10 on hand. We have 6 moles of O2 on hand. That's how much we actually have. So that's what we have to do the calculations for. And then we use the coefficients to generate our mole-to-mole ratios. All right, so anyway, that gives us 12 moles of CO2. Notice that moles of C4H10 cancel. All right, so now we're going to start over with that 6 moles of O2 and see how much CO2 that would produce if we use 6 moles of O2. Well, for every 13 moles of O2, there are 8 moles of CO2 produced. And let's see, I need my calculator for this one. 6 times 8 over 13 is going to give us 3.7 moles of CO2. And now we compare the two answers, and we notice that this one is smaller. And because it's smaller, this is the one that's going to be the real answer. Why? Because once you get to 3.7 moles of CO2 produced, all of your O2 has been consumed. That's what that means. The smaller value tells you which of the reactants is going to constrain or limit how much product you can get. So the smaller value is always going to tell us that this guy over here is our limiting reactant. Okay, so O2 is our limiting reactant, and C4H10 is present in excess. So I'm going to go ahead and note that up here, that O2 is limiting, and C4H10 is excess. All right, so I'm also going to, so that's the first part of the question, right? How many moles of CO2 are produced? We're also asked how many moles of the excess reactant remain when the reaction is complete. So in other words, how much is left over? All right, so what I'm going to do is I'm going to get rid of this calculation because this isn't helping us. We can ignore it at this point anyway because we've proven that that's not the limiting reactant. And I'm going to grab this guy move this up, okay, because this will be handy to have around and look at. Okay, so now we would like to figure out how much of the excess reactant is left over. This is a two-step process because we're going to start with, you can start with the 6 moles of O2 or the 3.7 moles of CO2, either one, something from the limiting step, something from the calculation involving the limiting reactant. And we're going to work from that over to the excess reactant, all right? And at some point, we're going to figure out how much of the C4H10 is used by the 6 moles of O2, and then we're going to subtract from the original amount to figure out how much is left over, how much is excess. All right, so I like to start with my 6 moles of O2. You may be more comfortable starting with the amount of CO2 produced. I don't care, you'll get the same answer every time, as long as you did the calculation right. Either one is fine. I'm gonna stick with the O2. And I know from my reaction equation that every 13 moles of O2 will react with 2 moles of C4H10. All right, so that means that 6 times 2 divided by 13, which is 0.92 moles of C4H10, are going to be used in the process of reacting with that 6 moles of O2. Okay, so this is also the number of moles of C4H10 that will produce this much CO2. It's the same calculation. You should get the same answer if you do it the other way. All right. So now, but that's not what I was asked. I was asked how much of the excess reactant remains. In other words, how much of it is left over? How much is in excess? So what I'm going to do is I'm going to take my 3.0 and I'm going to subtract my 0.92, and that's going to tell me how much is left over. All right. And for significant digit reasons that are not super important, but I'm trying to be more correct here, the answer here is 2.1 moles. If I haven't gone over this with you, we'll talk about it some other time. But this is going to leave 2.1 moles, of the C4H10 is in excess. All right, so that's how much is left over after the calculation. So let's look at this all over one more time. So we started with 2 different amounts of the reactants. We had to do the calculation twice. The smaller value is of the product is the one that actually gets created. So that tells us how much is actually formed. To get the excess, we take either the amount of the limiting reactant or the amount created by the limiting reactant, the amount of product created by the limiting reactant. We calculate over to how much of the excess is used, right? That's how much is used, and then we come down and subtract. This is the original amount, this is how much is used. The difference is how much is left over, all right? All right, let's do a practice problem. All right, let's say you have the reaction between copper chloride and aluminum, and that creates AlCl3 and copper metal. And to get this guy to balance, these are 3s, these are 2s. And let's say we have 10 grams of the copper chloride and we have 10 grams of the aluminum. And the question is, how many grams of copper actually get created? That's the first question. So how many grams of copper are actually produced? All right. And then how much of the limiting goodness gracious. How much of the excess reactant remains once the reaction is done, all right? So this is a practice problem. I'd like you to pause the video, get out a piece of paper, get your periodic table, get your calculator, try to work the problem, and then hit pause and then restart the video once you're done or once you're stuck and need some help, all right? So go ahead and do that for me. Okay, so now I'm going to go through the solution to this. So again, we've got two reactants with two amounts of starting material, so we got to work the problem twice. The difference here now is that we're in grams, so we don't have the easiness of the previous problem where everything was in moles. Now we're in grams, so we got to do grams to moles, mole to mole ratio, moles back to grams. So we've got 10 grams of the copper chloride. And the first thing we're going to do is go from grams of copper chloride to moles of copper chloride. Right? So we need to calculate the molar mass for copper chloride. So copper is 63.55 and chlorine is 35.45 times 2. So we've got 134.45 grams of copper chloride per 1 mole of copper chloride. All right, and my bet is that you knocked out this molar mass really fast, even though, a week ago this would have taken you forever. So I bet you're noticing now that you're getting faster at these. So now we're going to go from moles of copper chloride to, we're trying to get to copper, so we're going to go to moles of copper. And notice that that's a 3-to-3 ratio. You can call it 1-to-1 if you want. I like to stick with the numbers that are in the reaction. It just keeps me straight. And then 1 mole of copper is 63.55 grams of copper. All right, so we punch that through the calculator. And if I've done that correctly, that is 4.727 grams of copper. But now we've got to start over with our 10 grams of aluminum. Which, by the way, 10 grams of aluminum turns out to be a lot. We're going to do this as a lab, as you'll see. So 10 grams of aluminum, or that 26.98 grams of aluminum per 1 mole of aluminum. Now we're trying to get to copper, so we're going to do 2 moles of aluminum for every 3 moles of copper. And 1 mole of copper is going to correspond to 63.55 grams of copper. All right, punch that one through. Times 63.55 divided by 26.98 times 2. Remember to put your denominators in parentheses to make things work out better. Okay, that's 35.33 grams of copper. So the smaller amount then is the amount that's coming here from the copper chloride. So we know that the copper chloride is our limiting reactant. And we know that aluminum is our excess. Okay, so I'm going to go ahead and clear off this lower part here because we don't need that anymore. All right, and we're now going to do the second part of this calculation, which is how much of the excess reactant remains. Well, the excess reactant is the aluminum. So we're going to start with the 10.00 grams of the limiting reactant, copper chloride, and we're going to go over to aluminum and see how much that uses up. So this is 134.45 grams of copper chloride per 1 mole of copper chloride. And if this seems repetitive, it kind of is. It's okay. You're doing it right. 3 moles of copper chloride for every 2 moles of aluminum. Okay. But we need to do this in grams, so we got to go back to grams. So 1 mole of aluminum is 26.98 grams of aluminum. And that's going to give us 10 times 2 times 26.98 divided by parentheses 134.45 times 3, close parentheses. That gives us 1.338 grams of aluminum, and I always like to write myself a note that that's how much is used in the process. So now we take our 10 grams of aluminum we had to begin with, we subtract our 1.338 grams that are used, 10 minus answer, and that gives us 8.66 grams of aluminum that are present in excess. Okay, so I told you 10 grams of aluminum is a lot. So, and that's going to be, it's because it's a lot of moles of aluminum because aluminum is really light. So anyway, the amount of aluminum that's left over is 8.66 grams, right? So one last time through the process. If you're given amounts of 2 of the reactants, you got to work the problem twice. Whichever value is smaller is the amount that is, that's supposed to say smaller, I don't know how. Whichever one is smaller is the amount that's actually produced. That determines our limiting reactant. We then can use the limiting reactant to go over to the excess reactant, figure out how much of the excess reactant is used reacting with that limiting reactant. And then we go back and subtract. We take our original amount, we subtract how much is used, that tells us how much is left in excess, all right? It's a little bit of a process. You'll get used to it once you've done it a few times. You'll see examples of this in the lab as well, all right? All right, everyone, please feel free to leave me a question in the comments or get in touch, and hope this